In this presentation, we'll be covering the ACR controller's architecture for using masters and how it allows advanced motion through setpoint summation. I'll also explain the two basic types of motion of the ACR, both interpolated and jog motion. There will be examples of the more advanced motions and how they tie in with the masters. So let's begin. The ACR allows four types of motion. Single-axis profiling is used with the jog offset commands. This can be incremental distance or jogging to an absolute position, or jogging the motor continuously. This is similar to the 6K's go command in that if you were to jog multiple axes starting at the same time, they all have their own accelerations and velocities, so they wouldn't necessarily reach the endpoint at the same time. Second is multi-axis profiling. This allows interpolated motion of multiple axes. The velocity and acceleration is the path value, and the axes commanded to move are then interpolated so that they reach the end position at the same time. This uses the move command, and for circles or arcs, the circle clockwise, circle counterclockwise, sine, or three-dimensional arc commands. These are similar to the 6K's go L and parcom commands, except programmers aren't limited to two axes. Third, the ACR can also do gearing, where one axis can follow another axis. Somewhat related is the Gantry lock, where instead of following the other axis, it's receiving the same commanded position, preventing lag and orthogonality errors. Last, the ACR allows camming very easily with arrays. Arrays can be linked together and vary in the number of points. Multi-axis motion is made easier with the ACR9000 programming language. Here is an example of a machine with two parts. The first is a two-axis flying shear with belt-driven actuator carrying the material cutter with a load-mounted encoder. The other part of the machine has a rotary motor that is either material feeding nip rollers or could be printing labels onto material and then cutting the labels to length. The entire machine could be running on a continuous cam profile. From the ACR controller standpoint, this would be set up as two parts. The two axes of the flying shear would move together and be geared to the line-mounted encoder. So this part is one coordinate system, or in ACR terms, is a master. The second part of the machine is the printer nips and rotary knife. The rotary knife could be set up to follow the printer speed, ramping up to material speed to cut, then moving back to the starting position. This part would be a separate coordinate system, or again, in ACR terms, on its own master. In terms of the cam profile, this is stored as an array with the ACR9000 controllers. So each part of the machine or each master could be following that cam profile. Optionally, you could run these two parts separate from one another, or you could synchronize the masters with the sync command. Here is a different type of machine with two 3-axis linear positioners. These 3-axis XYZ systems could be linear or rotary servo, or stepper-driven in any combination. For interpolated motion, each system would have its own coordinate system. So the right-hand system would be on one master and the left-hand system on a separate master. Each system could be running its own type of multi-axis motion. Let's take a look at some of the advanced motion the ACR is capable of. Each of these XYZ systems at the same time could be running different parts. One example of motion is NURBs, where you define the points and a path is generated around those points. With NURBs, the path doesn't go through the points defined, but rather uses an industrial standard algorithm to evaluate the points and generate the path. Splines, on the other hand, is similar, with data points defined, but here the path generated must pass through those points. The ACR is not limited to two-axis motion, though, and can do three-dimensional arcs shown in this XYZ plot. Another common application would be an XY system, with the third axis as a theta axis. Here shows the advantages of the ACR's look-ahead feature that keeps the theta axis at a perfect 90-degree angle from the path. Even if the path reaches a point, it'll rotate the theta axis before advancing the X and Y. Pretty cool motion. You may ask, how does the ACR do it? I'm glad you asked. The heart of the ACR's advanced motion capabilities lies within the Setpoint Summation architecture. Each axis allows users to have multiple move types that can be commanded and with different sources. First, interpolated or coordinated moves use the trajectory calculated from the master. Second, you can also do gearing or following of another motion axis or an external encoder, or actually any ACR parameter for that matter. A common parameter for the Aries controller often used is a system clock, which is constantly running on power up. 3. Single-axis offset moves can be commanded with the jog commands. The jog profiler calculates its own trajectory. More on that later. 4. Cam profiling is very easy to do. Multiple cam tables can be set up and is an array of points. These 4 moves are calculated and added together to be the primary set point. In addition to the 4 types of motion, error correction can be enabled with both ball screw and backlash compensation. Together, these are summed as the secondary set point. The secondary set point is the commanded position. Simple applications can use one type of motion at a time, but the beauty of the ACR is in this architecture. Setpoint Summation enables the ACR to do advanced motion for customers' most demanding applications. Now, let's see first, how do you set it up? In ACR-View's configuration wizard, the axis screen allows you to set up each axis. Each axis can be configured as a DAC output for a servo, stepper output, or EPL for Ethernet Powerlink axes. Each axis can have an alias name. You may elect to use the default or change these. As programmers will repeatedly be using these when commanding motion, good practice is to keep these as short as possible, such as X, Y, Z, or T for a theta, or for 2 parallel axes you could use XR or XL. These though can be any name you want. The node ID is for the EPL axis and corresponds to the dial switch for the Aries-EPL for its address or address switch bank for the Compax3 EPL. The master is a pull-down selection and allows you to set the axis master. The ACR9000 is capable of handling 8 masters. Each master is a trajectory calculator and is associated with a motion program. Master 0 is running program 0. The axes are then attached to that master. The ACR9000 can have 8 axes of servos or steppers. With the Ethernet Powerlink, you may have up to 16 axes. This could be 8 axes of steppers and 8 EPL axes, or 2 axes of direct drive servos and 14 EPL axes. Each axis is a slave that is attached to a master. Note that the axis names, the aliases, are only recognized by that master. You can command motion from a different program, but would need to use the axis number and not the alias name. Also note that programs 8 through 15 share a 1 millisecond time slice and are non-motion programs. These non-motion programs allow you to run tasks continuously in the background, handling communications, monitoring inputs, and setting outputs, etc. Use INH inhibit command carefully in progs 8 through 15. If you inhibit one, all are inhibited until that bit evaluates true. In the motion programs prog 0 through prog 7, the INH inhibit command in one program does not affect the other programs, as they all have their own time slice. In the ACR-View configuration wizard, each master can have an alias name and is set with default units: inches, millimeters, degrees, revs, or any other units you'd like to use, meters, feet, etc. You can set the default values for the accel, decel, and stop ramps and velocity. If acceleration or velocity isn't specified, these values are used. Obviously, it would be a good practice to set these to a low speed value until the program is developed. Each axis, however, has its own scaling. The axis scaling screen allows users to define the mechanics connected to the motor shaft, if there's a reducer or lead screw, etc. As these values are entered, the scaling is developed and displayed on the bottom of the screen. This screen corresponds to the PPU, which is pulses per unit command. With the ACR demo with the BE motors with the J encoder, those are 8,000 counts post quadrature. If you wanted to program in revolutions, if you set the transmission type to none, it would then set PPU to 8,000 if you query that in the terminal window with PPU space X. If you had a 5 rev per inch ball screw and a sum to 1 reducer with a J encoder, this would be 5 times 8,000, which is 40,000 counts divided by 7. Note that what is actually downloaded to the controller is a numerator and a denominator to prevent any rounding errors. Even though the master may be in inches, a theta axis attached to the master could be set as 360 if you wanted that to be in degrees. The configuration wizard allows for the 9000's onboard DAC or stepper axis to configure the feedback. Axis with one motor would be set for the position feedback, and this resolution would be set based on the motor's part number on the prior screen. If instead this were a dual loop system and we're using a linear encoder connected to the 9-pin encoder 8 or 9 connectors or any of the other axis connectors, you'd set the velocity feedback to the primary motor resolution, and then the load-mounted encoder's resolution, either linear or rotary, to the position feedback. If a BE motor with a J encoder was used with the dado positioner with a 1 micron linear encoder, the velocity feedback would be set to 8,000 pulses, and the position feedback would be 1,000, since there are 1,000 microns per millimeter. Note that with the ACR demo, the 9040 can only have EPL axes. With the 9000 or 9030, axes can be servo, stepper, or Ethernet Powerlink. What are these screens actually doing? These attach the axis feedback and the output type. If you go to the program prompt in the terminal window and type attach, it'll display the slaves attached to that master program and the alias name. After the slave axis, first is encoder source for the position feedback, then the output type. Note for feedback stepper is valid and turns off the feedback being open loop. The output type is either DAC or stepper. Note EPL has both feedback and output. A dual loop would have a secondary encoder feedback for the velocity. For Compax 3 with load-mounted feedback, both loops are closed at the Compax 3, and the axis feedback would be set to the load-mounted resolution. For line-mounted encoders connected to the Compax 3 or Aries-EPL drives, those are read back as parameters that can be used as gear or cam sources. The motor connected would be a single loop using the default feedback resolution. Master profile moves are coordinated or interpolated moves. Let's take a look at this further. In ACR-View on the oscilloscope, if you click on the motion tab, you can see I've set the accel, decel, and stop ramps to 100 in terms of millimeters per second. The velocity for the trajectory is set to 10, and I'm going to move my x-axis 5 millimeters. So go ahead and press OK, and then I'm going to go ahead and run it a single time. I've set my time base to 200 milliseconds per division. Channel 1 is set in terms of the velocity term for axis 0. This is under the monitor parameters, and then channel 3 is set similar to channel 1 but is for axis 1 instead of axis 0. So channel 1 is for my x, channel 3 is for my y. Channel 2 is for the vector velocity, so that'll be in green. That is in terms of user units, so in terms of 10, that'll be 5 units per division. So you can see this comes out to be 10 millimeters per second. Channel 1, the velocity term is in terms of encoder counts. So since only my x-axis is moving 10 revs per second times 8,000 counts per rev, since I have a BE motor with a J encoder, that's 8,000 count post-quad encoder, that works out to be 80,000 counts. So I've set my scaling to 50,000 units per division on there. and you can see they both accelerate and stop at the same time, and the total time for the move is around 600 milliseconds. Now let's take a look. If I were to add a y-axis move under the motion, I can just go in, say y of 10, press OK. I'm going to run this a single time. So my x-axis is going to move 5, my y-axis is going to move 10, but they're both going to reach the final position at the same time. So it's just acquiring the data. So you can see the trajectory velocity is still 10, but the x-axis is now lower since it's only moving 5 revolutions. My y-axis is my channel 3 that has to move twice as far, so the velocity comes out to be about twice as much, but it reaches the end position at the same time. As an aside, there is a difference between deceleration and stop. The decel ramp is only used if the stop is 0. So this is used when doing a blended move, where you are moving at one speed, then want to decelerate to a slower speed. Setting the stop to 0 allows continuous moves to be commanded to different velocity values. Note that after decelerating to the lower speed, the stop ramp needs to be reset to the correct value. If it reaches the end position while stop is still set to 0, it will command an instant stop, which could be hard on your mechanics. In addition to the coordinated motion, users also have the jog offset motion available. These are single axis moves with their own accel, decel, and velocity commands, all still in user units. Absolute distance moves can be commanded with jog ABS, jog absolute. Incremental distances can be commanded with jog INC, jog incremental. If you want to jog the motor continuously, use either jog forward or jog reverse. To stop, use jog off. Note again, these moves are separate from the interpolated master moves, so you can jog at the same time as the coordinated motion. Similar to the coordinated motions, reset and encoder reset commands, the jog also has res and ren commands. The jog res without a number will zero the axis jog position, but then add the difference to the current position. You can also use jog res x10, and this would set the x-axis jog offset position as 10, and then add the difference to the current position. The jog ren goes the other way, allowing users to preload a value into the current position, adding the difference to the jog offset value. As a reminder from the status panel training session, the servo loop status panel allows seeing the entire setpoint summation for an axis in real time, and also gives the actual feedback position and the following error. This is helpful in seeing the coordinated current position moves in addition to any gear offset, jog offset, cam offset moves, which are summed to be the primary setpoint. Those are added to the ball screw and backlash offset to become the secondary set point, which is the commanded position. Gearing is the third type of motion and allows one axis to follow another parameter, whether that's another axis commanded position, actual encoder position, jog move, or any other parameter. The source sets the parameter the axis gear move is tied to. Common sources will be shown on the next slide. Gear PPU sets the scaling. Say if you had a 1000 pulse per revolution encoder post quadrature into encoder 8 or 9, this PPU would be set to 8000. Like the axis units, this can be set as an equation to prevent rounding errors. Then, just like jog, there's separate accel and decel ramps, and it is enabled with gear on and disabled with gear off. Gear res is the reset for the gear and allows this to be set to 0 or preloaded with a value. The difference is then added to the current position. If you wanted to gear X to Y, you could do this two ways: gear SRC X ENC1, or using the parameter number instead of encoder 1, gear source X P6160. On EPL axis, the encoder feedback is coming across the Ethernet Powerlink, not the physical encoder inputs. So on your demo, you could do gear source X EPL D1 or using the parameter number source X P12546. Some other common set points used is the secondary set point P12551 for the y-axis, 12544 for the current coordinated position, or 12553 for the jog offset value. Let's take a look at putting this all together in a program. Here's a sample program that gears an EPL x-axis 0 to an EPL y-axis 1. First, I want to define a local variable named counter, so this goes before the program line at the very top. Inside the program, dimension the local variable, enable the axis and reset their positions to 0. The gear source is set to Y, which is axis 1's jog offset position P12553. PPU is set to 8000 since Y's motor has an 8000 post-quadrature resolution encoder. Gear ratio is set to -2.5. The formula could be used for ratios to prevent rounding errors. Enable gearing and set the counter to 0. Start a label setting the jog ramps for Y, then do a single axis jog move of 10 units. I'll wait until the position is almost there with an IH pause, but timeout after 5.5 seconds. Time delay of 1/10 of a second, then go back to 0. Increment the counter by 1 and print the counter. Then loop 5 times and then turn off the gear and the jog. So let's go ahead and take a look what this looks like in the terminal window. Just clear this and do an L run. Do a Control Y to clear that, and then I'll do it again. And then my y-axis is moving back and forth 5 revs at about 2 revs per second, and my x-axis is gearing to it, moving in the opposite direction, moving obviously faster. And then with the L run, you're listening to the program while it's running, so you can then see the print statement with the counter and it's incrementing. Now let's say if your line-mounted encoder may roll back a few counts during operation or e-stop, and on recovery you don't want the slave axis to reverse because they're moving a web that's in tension. You still want to gear, but the ACR has a ratchet function. There are 8 ratchets available that can be used for gearing or camming. There are different modes for the ratchet. If you want to count both up and down, this would be mode 0. If you want it to ignore in the negative direction, this would be mode 1. But then as soon as the source moves 1 count in the positive direction, the geared or cam axis will move forward. If you want it to keep track of how far negative it goes but only advance after it's reached the original position from where it started to roll backwards, this would be mode 3. Let's take a look at a sample ratchet program. So the ratchet is similar to gearing structure, but the gear source is the ratchet, and you set the ratchet mode, which filters the ratchet source, which can be any parameter. So gearing is simply ratcheted with mode 0 with no manipulation or filtering of the source. The ratchet source for both X and Y are set to encoder 8, which is P6272, and the mode for the ratchet is set to 3 on both X and Y. Other than that, it's identical to gearing, where you set the scaling with the PPU and the ratio, then turn on the gearing with the gear on. Now let's take a look at camming. Camming looks somewhat similar to gearing, but instead of gearing to a parameter, you dimension the number of segments the cam will have, and then define those segments as an array of points. Enable the cam with cam on and disable with cam off. Reset the cam or preload it with cam res. Let's take a look at a sample program. Similar to the gear sample program, I'll be using a counter variable. I'll be using a second internal variable, so I've set LV to 2. Since the array table is in counts, I'm going to set my x-axis units to be counts of PPU 1, and then reset the excess position error to 1000 encoder counts. I'm using the CAM example 1 shown in ACR-View's help file under CAM electronic CAM. I can copy and paste the sample program into the program editor. Instead of segments of 500 and 1000, I've set my distance for the first segment of 4000 counts of my y-axis, which is half a rev. For the retract, which is segment 2, I have more time, so I'm going to use 1.5 revs to do the retract, so 12,000 counts. The cam source is the y-axis jog motion, P12553. Start the cam with cam on X, reset the variables to 0. Set the y-axis jog ramps and the move distance to 2 with a velocity of 1. Scroll down a little bit. I'll pause the program execution until the move is done with IH pause. Instead of moving back and forth, this axis will always move forward. I've created a local variable LV1 that increments the IH pause value. If this IH pause value wasn't incremented, it would only execute once, as the position would always be greater than 15,990 after the first move. Thus, counter would increment without waiting for the next move. So if I want to take a look at the motion, let's switch over to the terminal emulator. Let's see with the common status panel at the same time as well. And do an L run. It'll execute the move plus the camming, and then increment the counter and do it 5 times in a row. NURBs are an interpolated motion and stands for non-uniform rational Bezier spline, and is a method of defining free-form curves with few control points. The interpolation mode is set based on the NURB mode command and can be set based on time, which is mode 0, or other modes including smooth or linear interpolation. The path does not intersect every point, and NURBs are used in high-speed machining for better surface finish. Below is an example. Let's program a NURB with our EPL demo. Alright, first thing that we're going to do is go into the ACR user guide on the online help and type in NURB. You'll see the NURB command here. Go to the bottom of the page and you will see the diagram there. You don't need to change the PPU, so you don't need to grab that line, but go ahead and highlight everything all the way to the end. And then we're going to copy and paste it into our program. Okay, now go into the program editor. Prog 0, paste. You'll notice that the minus for some reason doesn't show up correctly, so go ahead and change that on the very last line. Go to the very top, and since we're starting at res x23 and y8, let's go ahead and add a line here that resets it to start at that exact position. Download. And if you go into the XY plot, go into motion, that was left over from previously. You'll just have run prog 0, check the checkbox to download to prog 0 when the run button is hit. We'll actually be running prog 0, and set the sampling. PC based sampling 50 seconds is fine, and go ahead and do a run. You'll notice on channel 1 I'm only displaying the one channel, and this is the actual position for axis 0, and then also axis 1 is the y-axis. And there is the first finger of the hand, and it'll keep running. The buffer will fill up and it'll restart, but it will actually complete. So again, the scaling for this is 50,000 units. And there's the thumb. Congratulations on writing your own NURB program. The cubic spline interpolation fits a smooth curve, exactly passing through the data points specified by the user. The data points can be non-evenly spaced. This is based on the clamped cubic spline algorithms, thus allowing the user to specify the initial and final velocity in the algorithm. Interpolation, like the NURBs, can be time-based or velocity-based. Below is the program for the graph shown on the right. Let's take a look at ACR-View and program our own spline. Okay, if we go into the ACR-View online help and just type in spline, go down to the spline command and go to the bottom, you'll see the graphic and the example program. Go ahead and highlight that to copy. You can do a Control-C to copy and paste. Okay, we're back into ACR-View. Go into the Pro 0, copy and paste. You'll notice that the minus sign for some reason gets cut off, so I would go ahead and fix that right there. In the program, you'll notice that the accelerations and velocities aren't set, so we'll go ahead and add some values here. Go ahead and download. And we're going to go to the XY plot, and under the motion tab we have run prog 0. For the sampling, we'll go ahead and set it to PC sampling 50 seconds, press OK. Divisions is 50,000 units per division. Go ahead and click run. So you'll see your Aries-EPL motors going back and forth, and there you start to see the curve complete. And we're done. 3-point arcs allows continuous motion between arcs. You just specify a start point, an end point, and an intermediate point. Below is a sample program for the path shown on the right. For my EPL demo, I've added a third axis as the Z. Let's program this. Okay, in the ACR-View online help, if you go into the search and type TARC, press enter, go down to the TARC 3D arc, and go to the very bottom of the page, you'll see the example there with a graphic. So we're just going to copy and paste this into our prog 0. Okay, to my Aries-EPL demo system, I've actually added a third axis, which will be my Z axis, and I've enabled that. So if I go into my program 0, paste the program, now you'll notice that the accelerations and velocities aren't defined, so I'm going to go ahead and add some values into here of 100 for the accel velocity. I'm going to set this to 10. STP is going to be 100, DEC of 100, and for jerk, for pure S curving in these values, it's going to be a CC squared divided by velocity, which works out to be 100. And then because this actually starts at a non-000 value for the XYZ, I'm going to have it go ahead and start at these same values here. So I'm going to reset that, and then after it's done, I want to turn off the three-dimensional arc mode. So at the very bottom, go ahead and do a TARC off. Go ahead and download. You'll notice in the message box on the screen below that an unknown command in line 150. So if we take a look at x10, y2, z minus 10, a2, that a2 is actually a typo. We're going to have that fixed in a future version of the help guide. So I apologize for that, but I guess we could just delete that out. And download. And we're good. So we can go into the XY plot, and the motion again is run prog 0 added to prog 0 when we press the run button. So you can see the X and Y coordinates, and then also the XZ plot as well too. So if you take a look at the graph or the numbers in the program, it's a little bit easier to interpolate from the program code, but that is what that laid out in two-dimensional. Automatic tangential orientation allows a third axis to be oriented orthogonal to two other axes. Below is a sample code for the graph on the right. Alright, let's go into the ACR-View online help and go into tang on. The tangent on command has the actual graphic and the sample program, so go ahead and highlight that and we'll copy and paste it into ACR-View. Alright, so we're back into prog 0. Again, we have a 3-axis system with the Aries-EPL. I've expanded my Aries-EPL demo by adding a third axis, which is the Z-axis. Copy and paste the program into here. You'll notice that there's no accelerations and velocities. We're going to go ahead and add some in here. This starts at SCC 100, DEC 100. Let's set the velocity to 30 so it'll proceed fairly quickly, and set the jerk to 50. And then after the tangential move is done, I want that to turn off. After it's complete, go ahead and download. Because the z-axis is always moving orthogonally to the x and the y, it's very difficult to visualize that on an xy plot. But if you go onto the xy plot, and you can run this as well too, these values are extremely high, so you'll need to increase the divisions to 5 million counts per division. To get the entire move path. On the z-axis, that's always moving tangential, so it's difficult to see how that's going to be. Really, for a demo, what you would want would be an XYZ linear stage system with that z-axis as like a pen to demonstrate that to a customer. With the tangential moves, what it does is if there's a point on the x and y axis, then it's going to add another move in between the two moves of the path, so it orients the z-axis rather than commanding an instantaneous jerk on that z-axis, which would be liable to trip that out onto a tracking error. Would also be very hard on your mechanics if you were machining parts. So it does have the look ahead feature on there. And then the buffer fills up and then it will reset on the graph. So if you go ahead and run that a little bit on your system, you'll see how that performs. Congratulations on running your first tangential program. Another advanced feature of the ACR9000 is the time-based move. Instead of setting the accel, velocity, and decel and stop ramps for each and every move, if you want to set time for the move to complete, use the tmov. This command automatically calculates the new master profile parameters to do the moves in the specified time. The new parameters, accel, decel, stop, and velocity, are not greater than the user specified value. In other words, the user can specify the boundary of the master profile, and the tmov commands will remain within this boundary. If the time specified is too short to complete the move, then a secondary master flag bit, master short time, is set to indicate that the accel, decel, stop, or velocity limits are hit. In this case, the move is carried out using the limit values. Here's a sample program showing tmov on. To activate, tmove of 0.5 seconds. I'm going to move the x1 in half a second. Then I'm going to move an incremental distance of 4 in a half a second. Then set the tmov to 1, do another slower move, the same distance, and then to absolute 7, and then turn tmov off. Coordinated motion, jogging, gearing, and camming comprise the primary set point. The ACR can also add backlash and ball screw compensation for the secondary set point. This allows for compensating for mechanics inaccuracies. Parker's precision grade tables and stealth gear heads come with error maps. Ball screw compensation allows for error correction not only over one rev like a cam table, but over an entire range of travel. Ground ball screws have an error over one revolution. Typical for a precision ground ball screw is 6 microns per revolution, and this is periodic over each revolution as the same side of the ball screw translates through the ball nut. But the ball screw will also have an error over the entire travel. Typical, it's not to exceed 8 microns over 300 millimeters of travel. So the ball screw profiler is a table for compensation for the periodic and linear errors, allowing higher accuracy positioning without the additional costs of linear encoders or the complexities of a secondary feedback. In addition, you also have the backlash compensation, which allows for hysteresis when reversing direction, such as belt-driven systems, gearheads, or non-preloaded lead screw systems. These are added to the primary set point, as you'd want this compensation done for any of your move types on the axes. The ACR9000 series controllers also has an advanced feature helpful in Gantry systems when two motorized axes are run in parallel. Many controllers require the X' axis to be set to follow the X axis. The X axis position is being commanded to move and has its servo period update, and the X' axis is set to follow this value, so it's always one servo period behind as it has its own update. Also, if you're trying to command very small incremental moves, then you could have one axis fighting the other, so tuning is an issue, where you detune the X', but that also decreases your force available. And depending on the stiffness of your cross axis can also cause orthogonality errors, as you have a crabbing effect with X' always slightly behind the X axis. The ACR9000's Gantry lock allows both motors to receive the same commanded position at the same time. In addition to monitoring its own axis error, it also receives the error from the other axis. This keeps both X and X' moving in parallel, preventing orthogonality errors or crabbing of the Gantry, and enables both motors to be run at full performance for high accuracy and increased machine throughput. This is the end of the ACR Motion Profilers training. Key points to remember are: 1. Masters are different coordinate systems, allowing independent and interpolated motion. 2. The different types of moves are added together with Setpoint Summation. 3. Jog moves are single-axis offsets.